All right, so what we're talking about today is angular momentum. So the camera's on a weird angle here, but don't worry about that. As long as we can see our uh, printout here, we're good. So angular momentum. Because for every linear concept, there is a correlated rotational concept. We are going to say the equation, or excuse me, the symbol for it is L, capital L, and with a vector sign, because like linear momentum is a vector, so is angular momentum. So if linear momentum, P, is equal to mass times velocity, I think it should make sense then that for a rigid rotating object, L is equal to, well, the counterpart of mass would be I, right? Because this is inertia from a translational sense. This is inertia from a rotational sense. And then rather than V, it's going to be omega. So whatever the direction of the omega vector is the direction of the L vector. So once again, remember, I can curl my fingers in the direction of the omega. Let's say if something is rotating around counterclockwise, the omega vector is out of the page. Therefore, the L vector is out of page. So that should make sense from that perspective there. And what is angular momentum? Well, in the same way that linear momentum is a relative measure of how hard it is to stop something that's translating, this is just a relative measure of how hard it is to stop something that is rotating. So that's all that the number means. So there we go. Not very interesting in terms of that. But in the same way, what was interesting with momentum was the conservation of momentum. So we figured out is momentum was conserved in the absence of net external forces, because we found to change momentum required a net external force. In fact, we found out that the net external force average on the system, or net external force on the system, was actually the derivative of momentum with respect to time, meaning that if momentum was changing over time, a net external force was doing that change. Similarly, here, we're going to have, rather than forces causing changes in translational motion, it should make sense then that net external torques are going to cause changes in angular momentum. So those are the correlated concepts there. So another way that we can write this here is if we want to do this not with calculus, we showed the impulse momentum theorem was that the impulse was equal to the net external force. And if I'm not doing derivatives here, I have to do average, and then delta t. Very similarly here, we would have that the change in angular momentum would be the net external torque average times delta t. So I need net external torques to change angular momentum. I need net external forces to change linear momentum. And that we found then, in the absence of net external forces, that if that was equal to zero on a system, then the initial linear momentum was equal to the final linear momentum. Similarly here, when net external torques are equal on the system are equal to zero, therefore the initial angular momentum of the system is going to equal the final angular momentum of the system. Okay, that's the concept. There's going to be some, specifics here that we'll look in terms of this, and let's hope that this makes sense. But that's the general gist so far. In terms of units, angular momentum, well, we know that I is kilograms meters squared. Angular velocity is radians per second, so the radians kind of hides in place there. So it's a kilogram meters squared over second squared is the units of angular momentum. Now, so let's talk about some ideas with angular momentum conservation, right? So classic examples. So the conservation of angular momentum. And the first set that we'll do are systems with fixed axes. So I don't know why. Let's say A, systems with fixed axes. So the classic example here that you have is the figure skater who is twirling, right? So here and I can change my moment of inertia by changing the shape. We know that figure skaters move their arms in and out. So if I have here a figure skater with their arms stretched out and they are rotating like this, that if they move their arms inwards, okay, right? So this is a terrible picture. They will spin faster. So if that's omega initial, that's omega final. Here's I initial, I final. And so here, why is the net external torque equal to zero? That's the big question. Well, if I look at this from a top-on view, what's happening? So this is the figure skater's hands. The axis of rotation is, so this is a top view, the axis of rotation is down the middle of this person and they're rotating like this. In order to move their arms in, they're going to exert a force directly inwards towards the pivot. So here I would say the net external torque is equal to zero because there's literally no torque, right? Because torque, we said, was equal to either R cross F, right? Or the magnitude of torque was the magnitude of the r vector, the magnitude of the f vector times the sine of the angle between them when they're drawn concurrently, or simply it was force times the lever arm distance, where the lever arm distance is the perpendicular distance from the axis of rotation to the line along which the force acts. No matter what you do here, because the r vector would be out this way, the f vector would be this way, that if you look at the angle between those two vectors, it would be 180, sine of 180 is 0. Or if you think about it here, the lever arm distance is 0 because these are horizontal forces, and the vertical distance between the axis of rotation and where the horizontal forces act is 0. Because the forces act through the pivot, the torque is 0. Okay? So this would be a situation in which I would do Li is equal to Lf. Therefore, I would have that I initial omega initial is equal to I final omega final. Boom, and then I do it that way. So any rigid rotating object that changes its shape over time, as long as that shape change is happening because of something internally, what's going on, and there's a lot of different examples of this. If I have a star, there's something called a pulsar, and that pulsar grows and shrinks due to gravitational forces. Once again, those are gravitational forces that all act inwards through the axis of rotation. For that system, the moment of inertia would be the moment of inertia changes, and therefore the angular momentum is constant throughout, and then this I and omega trade-off, right? But there's more interesting examples of this, and still systems with fixed axes. Let's assume I have a merry-go-round. This is a top view of a merry-go-round. There's my axis of rotation. It's right at the center of the object, and this thing is free to spin. Now, if I have a kid run along here and then jump on the merry-go-round, what would happen? Well, I think we would all agree that that kid and that merry-go-round would start to rotate. So here we have this very weird situation in which the kid jumps on here, and initially, let's say the omega of this system is 0, or of the merry-go-round is 0. But this kid is moving in a translational sense. But afterwards is not moving translational anymore, is moving as part of that merry-go-round. So what's going on there? Well, it so happens that we can conceive of this. Well, let's see. In terms of angular momentum, right? It'd be weird to talk about this thing having angular momentum, but I'm going to argue that it does, even though this thing is moving translationally initially. And the argument is very simple. When the kid jumps on the merry-go-round, there is a force on the merry-go-round that is like this. So this is the force of the kid on the merry-go-round. But simultaneously then, here's the kid. There's got to be a force of the merry-go-round on the kid. So the kid's going to slow down to some perspective because of that force and kind of like stick on it. And the merry-go-round is going to move like this. But if we think about this in terms of torque, the kid actually is going to exert a torque on the merry-go-round, and you could think of this as a torque on the kid. So because if we look at our condition here, there are torques, But here, they are not external to the system. They are internal to the system because it's the torque of the kid on the merry-go-round and the merry-go-round of the kid, right? So I still meet the condition, meaning the initial angular momentum has to be the final angular momentum. Now, this final bit is easy because this is just I of the system, omega final. But that means that the kid has to have angular momentum initially in order for this analysis to work. So what we're going to do here is we're going to make an argument for what is the angular momentum for an object moving a point mass that is moving linearly, right? Just a little sideline here. What would be the I system finally? Well, that would be the I of the kid plus the I of the merry-go-round. The I of the kid would just be a point mass, right? And the merry-go-round, let's say it's a disk. If you 1/2 m of the disk, r of the disk squared, right? So that's pretty simple to find. But what we want to find out now is the angular momentum of a point mass in translational motion. Now, the weird thing about this is that we still have to know what the axis of rotation is, or the axis we care about. And so here, if this is my axis of rotation, and here's my mass moving translationally like this, right? The way that we're going to do this is we're going to make a parallelism argument. Torque was R cross F, which ended up being, as we said, the magnitude of torque was RF sine theta, where theta was the angle between the R and the F vector, or torque was force times the lever arm distance. We're going to do a very similar argument here, where L is going to be R cross P. It's linear momentum, right? Or the magnitude of L is equal to RmV sine theta, where theta is the angle between the R and the V vector, or just L is equal to mvL perpendicular, where L perpendicular is the perpendicular distance between the line along which the object is moving and where the axis of rotation is. So let's look at all of these things. So here we go. In this perspective, that would be my R vector, right? And so when the mass is here, there's my velocity. That is my R vector. When the mass is here, that is my R vector. Notice here, I just have this object moving in a straight line. You may think, well, hold on, R is changing in length. That's problematic. But I'm going to tell you the angular momentum of this object is constant. Well, what's going on there? Well, if we look at the angle, though, the angle there is also changing, right? So there's the momentum vector. There's the R vector. Here is the momentum vector. Here is the R vector. So this angle is changing over time. But if you think about what the R sine theta does, what is R sine theta? R sine theta is just this perpendicular bit here, right? And so if you notice, that's the same. That's what L perpendicular is, folks. It is the shortest distance between the line along which the point mass is moving and the axis of rotation. So there it is. I'm going to tell you for an object, a point mass moving in translational motion, this is the winning way to do it. We're going to draw a dotted line representing the velocity, the line along which the velocity would act, and then find the shortest perpendicular distance between that and the axis of rotation. So since this axis of rotation is fixed, here, interestingly enough, this object moving in a straight line has a constant angular momentum with respect to this axis. Now you might say, like, but that's pretty arbitrary because if I move the axis, L moves. Well, yeah, that is absolutely true, and I can arbitrarily choose the axis. But in a problem where there's a defined axis, it's not arbitrary. That will matter. So, for example, going back to here, this would be the mass of the kid, the initial velocity of the kid, and the L perpendicular here would just be the R of the entire merry-go-round. Now, if this kid was to go like this, you would note, and they jumped on right here, that would not cause the merry-go-round to start spinning, right? Because here the L perpendicular would be 0 because the velocity is acting through the axis of rotation. It also jives pretty well with hopefully your understanding of what would happen on a merry-go-round. Now here, if the kid was here and jumped on at the edge here, well, that is going to create motion. But if you notice, the angular momentum would be the same as up here because this distance would be the same, except this is going to get the system to rotate clockwise, and this would get the system to rotate counterclockwise. So the important thing about this version of the equation is that when we're doing this version of the equation, folks, it is really important that we understand we're finding the magnitude, and then we're going to use common sense in order to turn it into the vector, right? So if I say clockwise as positive, I would say that this thing has an L vector of m of the kid v r positive, and I would say this would have a negative m kid v r. I would assign it a sign rather than have the math come out. Now, there's a way to do all this with cross products, but that's not very helpful for the AP exam, right? It's very clear in terms of what we're going to do on this, right? So that's how we do this. Now, we could do the opposite problem. If the kid is on the merry-go-round and jumps off, right? Well, if I look at this initially, the merry-go-round and the kid have an angular velocity of 0, and here's the kid on there. If the kid just jumps off the merry-go-round in this case, hopefully what you'd see is this merry-go-round would start to rotate in the opposite direction. Yes? Because angular momentum would have to be conserved. There'd be no net external torque because the torque between these two things would be internal. And so therefore this would be 0, and therefore L final of the kid plus L final of the merry-go-round would have to equal 0. So one would have to be positive, one would be negative. If I assign this thing to be positive, this would be a negative, that would be a positive, and there you go, right? Or even, it doesn't even have to get off. If the kid tried to walk around this way, if you ever tried to walk in a merry-go-round, the merry-go-round goes in the opposite direction, which is kind of neat. Now, sometimes it doesn't because of friction with the pivot, which would be a net external torque, and so no bueno. So there we go. The next section of this is talking about what happens if I have a non-fixed pivot. And I'm going to do this very quickly because this is generally not something that's done on the multiple choice, but I want you to be aware of it if it is going to happen, because it's fairly complicated. Let's say I have, I don't know, a stick, and that stick is free, right? It's not constrained in any way, right? If I were to have a kid, let's say I have an ice skater. An ice skater is going to skate along and grab the stick. Okay, now that stick has mass, and so we know that the center of mass of the stick is here, center of mass of the kid is there. Let's assume the kid is a point mass. So when this kid grabs that, what's going to end up happening is that the kid and the stick are going to not only translate, but they're going to rotate. And sort of weird to think about, because if this was constrained here, very simply, off it would go. If this was constrained here, then it would just rotate like that. But the question here is, well, what happens if the stick is not constrained? Well, we said for a non-fixed pivot that systems will always rotate about their center of mass if not constrained. So the weird thing here is we would have to imagine once the kid is on the stick, right, what happens from there? Well, what would happen from there is that this would have a system center of mass that'd be somewhere between the kid and the stick. And so I would have to first find where that center of mass point is. Like if the kid was really massive compared to the stick, it'd be closer to the kid. If the stick was really massive compared to the kid, it'd be closer to the center of mass there, but it's going to be somewhere in between the two. So what's going to happen here is that this system would rotate about this point, right? And so you may come along here a little bit later and you'd see it's like made half a rotation, let's say. Oof, that's terrible. But this is what it looks like as it's rotating through. Now you will note that what I did was the center of mass of the system is going to be moving at a constant velocity, right, in a straight line, even as the system rotates about that center of mass point, right? And so this ends up with a collision between a point mass and a free object. What we would say is two things are true. We would say the momentum is conserved of the system because the net external force on the system is equal to 0, right? That means that the VCOM is constant, right? So since this thing is moving initially, the system center of mass is somewhere in between them is moving as well. It will continue to move. We would say that the angular momentum is conserved because the net external torque is equal to 0, right? Because the torques are internal. And that would mean here that it rotates about system COM, right? This energy would not be conserved in this interaction because you have functionally a change in shape as two things come together. This would be a perfectly inelastic collision in two dimensions, right? And so that's how you deal with this when there's a non-fixed point. And the math of it gets actually really quite complicated because the first thing you need to do is find the center of mass point. Then once you do, then you use the L perpendicular for that new point. But that's unlikely to happen on multiple choice questions from a mathematical perspective, much more likely to happen from a theoretical perspective, being able to say, yes, angular momentum is conserved and linear momentum is conserved because the forces are internal, the torques are internal to each other, and there you go. And then energy is not conserved. That's actually a fairly common question where they'll say, here's a given situation, is linear momentum conserved? Is angular momentum conserved? Is energy conserved? So I want to end this video by just going through that one more time, right? Momentum, L, and E. The condition here is that the net external force of the system is 0. So first off, are there internal forces within the system? Remember, a Newton's third law pair are going to make internal forces. So you ask yourself, are there forces external to the system? So if there is a constraint on the system, like a fixed pivot, that means the net external force on the system is not equal to 0. So anytime there's a fixed constraint, linear momentum is not going to be conserved. So you have to have, once again, free objects if we're going to have linear momentum to be conserved. Angular momentum, net external torque on the system is equal to 0. So the first question we ask ourselves, does the force causing change cause a torque? If that force acts through the axis of rotation, the answer is no. I don't have to access the whole idea of internal versus external. There's just literally no torque, right? And then is it an internal torque or is it something from the outside acting, right? If it's the torque of one thing on another on one thing, then angular momentum will be conserved. So you have to ask yourself both these questions. If there's no torque, then angular momentum is conserved. If there are torques, but they are internal, angular momentum is conserved. Now remember, energy, work, non-conservative is equal to 0. The only thing that matters is, are the forces conservative or not? Doesn't matter what else happens. Is the force conservative or not? Remember, gravity is a conservative force. The elastic force is a conservative force. The magnetic force is a conservative force, right? Applied forces are not conservative forces. Collision forces are not conservative forces unless they say there's a spring, a Hooke's law spring in between them, or there's magnetic bumpers or something, right? So this is a very common AP question. Know when things are conserved and when things are not conserved. And that is what you need to know about angular momentum for the AP exam.